Okay, I think yeah, everything is good. Just give me one moment.
Sure, yeah.
Okay, so today we will start with the distributed transactions and consensus. So last time we discussed a little bit about two-phase commit. This time we will go in more details. So, okay, so basically, what is distributed transaction? It is basically a transaction which is spread across multiple nodes in a distributed network, right? And so just thinking about that, what are the situations when we would need distributed transaction? So let's say your data is partitioned among multiple nodes, right? And your transaction consists of updating data across those multiple nodes, right? Then that means your transaction is a distributed transaction because uh, it should succeed when it succeed on all of those nodes, right? And and basically, as we have discussed in chapter 7 before, that a transaction should follow all the asset properties, right? So like an example would be like, let's say I have two different database in two different nodes, one in which I have a product count and in one I have customer orders. Then if a customer buys a product, right, I have to both decrease uh, the product count, and I have to add that product to customer orders, right? And both of the things should succeed at the same time. Like if one of them succeed and another does not, then we might have our system in an inconsistent state, right? So, so yeah. Uh, so now, like before we actually see how we can implement uh, distributed transaction, first, like I wanted to just revise again that how would we actually implement a transaction on a single node? Uh, so, like anyone has any ideas how is a transaction actually implemented on a single node? On a single node, if we have to update two rows at the same time, how does a transaction happen in that case?
Yeah, I think we have two options. The first option is pessimistic approach. It means we have to walk row, and another one is optimistic approach. Yeah, so if one transaction will see that rows is changes, it will be aborted eventually. I am talking about optimistic approach.
Okay, so the thing you are, yeah, that is one of the things in transaction. So uh, what you're talking about is like if two transactions are happening at the same time, how do we prevent them to modify each other's data, right? And follow the I property of asset isolation, that if two transactions are happening at the same time, they should be isolated, right? And the isolation property could be achieved either by locks, right? By taking the locks, or by by doing this optimistic locking, right? So that is one thing. But how would we actually implement atomicity and durability? So by that, what I mean is that if a transaction wants to update two rows, right? Or in a database, on a single database, there are two different tables that it wants to modify. How will a transaction ensure that both of them should happen, and then only your transaction should succeed? uh, like if one of the transaction happens, your database should not be in a state that only one of the transaction happens. how do we ensure that? So like, let's take the example of pessimistic locking, right? We said that transaction could be achieved by pessimistic locking, but think of this scenario. So we had to update two different rows, right? And uh, so like, let me go here. So let's take this example, right? We had to update, so we had this key 1 as 5, key 2 as 7, right? Now, in my transaction, I'm saying that key 1 should be incremented by 3 and key 2 should be incremented by 4, right? So basically this should become 9, this should become 8, this should become 11, right? So now, like going by the pessimistic locking approach, so the database will take lock on both of these rows, right? And now, so the database has taken lock. Now the database updates this to 8, right? And let's say now the database has updated this to 8, and now our system crashes. So if now our system crashes and system wakes up again, we will see that this row has been updated to 8, but this row was still 7, right?
Yeah.
So how do we actually prevent this scenario from happening?
Yeah, we will have a flag in order to mark transaction if it's completed or not, and send data before and send data to write ahead log
Yeah,
for durability.
right. Yeah. So yeah, exactly. So what we will, so like, so the steps which would generally happen is like when a transaction has to start, basically the database will take locks on these two rows, right? And it will also start appending data to val. So in val, it will say that some ID transaction is starting. So this is the transaction ID. In this transaction, I want to update key 1 from 5 to 8. So it will save the previous value as well as new value it's want to save, right? And then it will update 5 to 8. Then it will say key 2 will be updating from 7 to 11. So, and then this will be updated from 7 to 11. And then it will append a commit record. And once the commit is appended, then it will return success to the user. Okay, so now let's say in this situation, what will happen if a machine goes down? And one more thing, another thing we are saying is that uh, whenever machine goes down and it comes up again, before actually serving the customer, it has to look at the val and it has to see that there should not be any pending transaction. If there is any pending transaction, it should be reverted before the database could actually serve the customer, right? So we have implemented this logic in our system. So so at this point, when the transaction started, key 1 was updated from 5 to 8. So this was updated from 5 to 8, and now our system crashed, right? So we had only this value. Now, when the system will wake up again, it will have only logs up till here, up till this point, right? So it will see that this transaction 1 to 3, it was in incomplete state because it did not had commit record. If a transaction has a commit record, that means it was successfully completed. But here, a transaction was only up till here. So then it will revert this and it knows what was the previous value. So it will revert this to previous value. And now once this is reverted, then the database will be available to the customer again. So now we will see that our system is in consistent, is in consistent state, and it has followed the atomicity property, right? That either everything happens or everything does not happen. Like we never reach this partial state. So like we have seen that val is this right ahead log is helping us satisfying this atomicity property, right? If we have to do two or more operations on a single node. So now let's move ahead and see how we can now implement a transaction on distributed system where there are multiple nodes. Before we move there, any comments or any questions? Okay. So yeah. So now let's move to this two-phase commit, right? So the idea behind two-phase commit is that uh, we want to update data in these two different nodes, right? And so how this works is the approach of two-phase commit that so the application first it will write the data to both of these databases, right? It will only write the data, it will not commit the data. And the commit stage, right, when actually we will commit the data, now that is split into two steps. One is prepare step, another is commit step, right? So in prepare step, uh, the so we will have another component called coordinator. So in prepare step, coordinator will ask both the nodes if they can definitely commit the data or not. And it will then get the reply from both of these, right? And if both of these say yes, then the coordinator will store in his write ahead log that this transaction has to be committed, and then it will send this message to both of these databases. And then as the database receive the message, they will commit the message, right? So now, like, let's see overall points of failures and various situations, like how things, if things break, how they're solved, right? So one thing that happens in this two-phase commit is that up till this point, when these two databases have not replied yes to the prepare stage, up till before this point, they can anytime revert their uh, write of the data, their transaction. They can abort their transaction at any time, right? But once they have replied yes, then they no longer have the right to abort the transaction. Then, if the coordinator says that the data has to be committed, then they have to commit the data. So after this point, they have to wait for the coordinator, and if coordinator says like commit, then they have to commit the data. But like as you will see, like overall during this process, your rows are logged. So the rows are logged up till here. So that means that like once they have both the databases have written the data, still this row is not available, it's logged. And once they have replied yes to the prepare stage, then also these database nodes are not sure whether the data will be committed or not, because it could have happened that this node could have replied yes, this node could have replied no, then the coordinator decision would have been abort, and in that case they had to abort and roll back their transaction. So in so that's why until the final decision is made whether the row has to be committed or not, these rows will be in the locked state, right? And so basically again, the thing we are saying here is that once the coordinator has made its decision after hearing from both the databases, right, then it will save this in its log, and then it is the responsibility of the coordinator to send that message to these databases. And if any of these databases is unavailable, then it will keep on retrying multiple times until that database is up again and it can successfully send the message, right? So so basically just like let's go over the steps one by one, how they're mentioned here. So when application wants to begin transaction, it requests the transaction ID from the coordinator. So first the application will request a transaction ID. Then the application begins single node transaction on each participant and attaches global unique ID to single node transaction. Coordinator or any of the nodes can abort up till this point. So this is this point when the application will like write data on these individual nodes, right? But again, this data is still not committed. It has just written the data. So now when the application is ready to commit, then the coordinator will send a prepare request. So the coordinator will send a prepare request to all the nodes. So when the database replies with yes, it has to make sure. So it has to append that data to its write head log and everything it has to do to make sure that after this point, if the coordinator says that commit, then it should be able to commit. It cannot abort after this point. So when the coordinator accepts prepare request, it makes uh, sure it can definitely commit transaction under all circumstances, right? Participant has made a promise, but not yet committed. When coordinator receives response from all prepare request, it makes a definite decision on whether to commit or abort. The coordinator must write this decision to its transaction log on disk so that it knows which way it decided in case it subsequently crashes. This is the commit point. So this will be the commit point. Once coordinator decision is written to disk, commit or abort request is sent to all participants. And then in this case, coordinator must retry forever until it succeeds, right? So basically, if the database goes down, right, after this point, whenever it will come back again, it will first talk to the coordinator and ask if there was any pending transaction for which I need to know the decision. And since the coordinator will keep on sending uh, sending the decision to these databases, so then it will send the message that for this transaction 123, my decision was commit, so you can commit and unlock the rows, right? Uh, so this is how like we can handle like failures in any of the nodes, right? So basically at before this point, if any of the nodes would have failed, then the coordinator would have made its decision to abort, right? Or if like before this point it fails and this database does not hear from coordinator, then as we said that before this point they are free to abort the transaction, so they don't even have to hear to the coordinator. Like before replying yes, if they are, if they have not heard back from coordinator, they can freely abort the they can freely abort this transaction, right? But after this step, they have to definitely talk to coordinator and wait for his response, and they cannot abort after this point, right? So now one problem here is like after this point, yes, right? After they have replied yes, what if the coordinator itself dies? So now if the coordinator dies, then the thing is that like because these two databases, these rows are waiting for the response from the coordinator, so they will be in the locked state forever until the coordinator comes back again alive, right? So this is the problem with two-phase commit, that basically this coordinator is a single point of failure. If it dies, then basically these rows will remain locked in the state in that state, right? So yeah, so this was about the coordinator failure, that if coordinator dies after this point and the transaction was not completed, they are stuck in locked state and those rows of data have uncertain data. So they will remain locked while the time being the coordinator recovers, right? Again, like if the coordinator would have died like at this point, then these nodes were free to abort uh, it. So the point is, if it has crashed after this point, now they don't know, because now they don't have the right to abort their transaction. So yeah, so this was about two-phase commit.
Abhishek, I would like to add something to this.
Mm-hmm.
So in the view of MySQL, so let's assume this database 1 and database 2 are the MySQL data instances. So in that case, a general question might come to our mind is like, when we say prepare, like which SQL command to use, right? When we say commit, which SQL command to use.
Mm-hmm.
So for that one, MySQL has we have to enable a separate package called XA architecture package. So
Mm-hmm.
what that does is it enables an XA transaction. So you get new set of statements. So when the coordinator is going to say it for the database 1 and 2 that prepare, so in that case it is going to say in the SQL that is going to write is XA prepare and for both of the databases, and when
Mm-hmm.
it wants to commit, it's gonna write XA commit.
Oh, okay, okay, nice. Okay. Yeah, yeah. Thank you so much for this info. Yeah, we are going to discuss about XA transactions, but yeah, like the exact commands which we have to execute. Yeah, I didn't know that. Okay, so nice. Okay. Okay, so let's actually, that's a good point. I think XA transactions directly related to this. So first, let's discuss this, then we can discuss all of these. Uh, XA transaction is actually a standard for implementing two-phase commit across heterogeneous technologies. Uh, so and so by heterogeneous, we mean that like we have two different databases. Like we could also use this to implement transaction on a homogeneous, like when both of them are SQL, or if they belong to a different company, like if they are like one is SQL and one is, let's say you have a message queue. If you want to implement a distributed transaction among a message queue and a database, then you would need to implement this XA transactions. So the my question is like MySQL and all, they, if we are doing a distributed transaction among the same database, don't they have like inbuilt something that you can just say like you have to implement on your own XA transaction? Because at least in this book they have mentioned that like XA is generally used for heterogeneous when they belong to different companies.
I don't have that idea, but whatever I knew, it was like even if you want to do in both the databases
Mhm,
at the same, even they are MySQL databases, but
mhm.
they are different. You need to use XA.
XA transaction.
But again, like now, since you asked question, I'm not sure. Like,
Mhm.
is that the true or not?
Yeah. Okay. Okay. Got it. So basically, like, and this XA is supported by many relational databases. So what happens is actually, like, so the database will expose this XA API, and the responsibility of coordinator lies in the application. So like the application, so this is the part of the database that database will reply yes or no to prepare and commit, but the part of coordinator will lie in the application. So how you will build it in your application is that you have, so the database will expose an interface and the application has to implement that interface. And basically in that interface, you have to implement the role of the coordinator. So basically, uh, the application has to implement coordinator by implementing this XA API. This transaction coordinator library hence is loaded in the same application as application issuing the transaction. And so basically it will keep track of all the participants in the transaction, get their prepare vote, and uses a log on the local disk. So now this part where we have to store the final decision to abort or commit, it will be stored in that application's local disk, right? and and then like once the application has made the decision, it will say it should commit, right? So now like again, like as you can see now, this is a part of coordinator, like the coordinator is part of application, so it has its own disadvantages. And so those limitations we will discuss when we come here, but let's quickly uh, discuss some other topics which are related to this two-phase commit. So one thing that was briefly mentioned in the book is three-phase commit. And uh, there were not many details mentioned about three-phase commit, but they said that since two-phase commit is blocking on the coordinator, alternate approach has been suggested, which is three-phase commit. But the problem with three-phase commit is it assumes that the network have bounded delay and the nodes have bounded response time. But as we know, like it's hard to find these kind of systems which have bounded delays and bounded response time, right? So most of the systems are built on commodity hardware, which where we don't have bounded delays and bounded response time. So that's why we cannot apply this three-phase commit over there. Then the other thing, uh, yeah, the other thing was that basically in practice, if we want to implement distributed transaction, there are two types, like basically homogeneous and heterogeneous. So one is this homogeneous is database internal distributed transaction. So this internal transaction are among nodes of a same database, like same SQL database. So these are easy to implement and optimize, and basically the database vendor would have done something to optimize these distributed transactions. But another scenario is heterogeneous distributed transaction, when the participants are from two different technologies, right? So that is called heterogeneous. Uh, then one more brief topic is like, so exactly once messages processing. So basically with this heterogeneous distributed transaction, it allows us to integrate uh, two different types of database into one transaction, right? So like, let's take this example that you have a message in a message queue, right? And that message has to be delivered to some database. So basically the database vendor has Hello, am I audible? I think my mic stopped. Hello.
Yeah, you are audible now.
Okay, great. Yeah. So so basically this discussion of exactly once message processing. So imagine a scenario when you have a message queue, and uh, and then you have to deliver that message to a database. So now your transaction will be completed once the data has been once that message has been delivered to the database, right? And it has been committed at the database. And also when the message queue has received an acknowledgement, right? Then your transaction gets completed. Because if the message queue does not receive acknowledgement, then the message queue will keep on retrying. It will think that this message is not yet delivered, so it will retry. So basically, if we want to do this exactly once message processing, then one way to do is we can implement a distributed transaction among this message queue and database, where one transaction is write to that database when the write gets committed, and another is when we get acknowledgement from the database in the queue. Right. So, so yeah. Okay, and then we have already discussed this, right? That so basically these nodes have to keep on holding the logs uh, if the coordinator has crashed, because they don't know what to do with this data, whether to commit or abort the data. So so once the coordinator recovers from failure. So when the coordinator recovers from failure, all these orphan and in doubt transactions could occur. So basically, like what was mentioned here is that since this the role of coordinator lies in application. So imagine a scenario when the coordinator crashed after this point, right? And also the log, in the log, whatever it has saved, that data got corrupted or it got lost, or because of any software bug, that data was not in the right state. Then this rows will be in locked state forever, right? So basically, database would not lock these rows forever. After some point, like they will either use some, like it depends on the database, but like some of them they use some heuristics or something to finally come to a conclusion if they don't hear back from coordinator after some specific time. So so yeah, so this was this. Yeah, okay, now the thing, limitations of distributed transactions, right? So the limitations, as one can evidently see, like everyone can see, this coordinator is a single point of failure. So if this is not replicated, if your log is lost over here, then you don't know like whether the transaction was actually atomic or not, right? And you don't know whether the heuristics that the database took, they're actually right or not. So yeah, so if the coordinator is not replicated, then it's a single point of failure, right? The other thing is that basically these server-side applications, right? These server-side applications, they are made stateless, and uh, one of the main reasons of being stateless is that you can add and remove nodes which are serving as your application server at any time based on the load and based on the traffic, right? Uh, but now imagine if your nodes are serving the role of, if your application servers are serving a role of coordinator, then in that case, they no longer are stateless because they are saving the state. They're saving the state of what was the decision, right? So basically, if your nodes are acting the coordinator in this case, they are no longer stateless. Then the other thing is like basically like in this situation when you are using XA transactions for heterogeneous distributed transaction, then XA is the lowest common denominator. So now like imagine all the problems which can happen with locking. So let's say if there were two transactions, right, and these two databases were implementing XA, and so one transaction first takes a lock on this row one, right? And then it now is now the application says take lock on row two because I want to do something. But before it takes lock on row two, another transaction takes a lock on row two, right? And then that is waiting on row one, right? So we have two transactions. One is waiting row one, row two here. Another one is also waiting on row one and row two here. So we can end up in a deadlock scenario where first transaction takes a lock on this row first and another takes a lock on this row first, right? And basically to find a deadlock, right? Those things are implemented within a single node. Like databases have mechanisms to find the scenarios of deadlock within a single node, but between multiple nodes, most of the databases don't have that support. So in because if we want to detect deadlocks among multiple nodes, then the database has to send these messages across these different nodes that what nodes has been logged, what nodes they're waiting on. So all this kind of stuff, right? Which is not implemented in most of the databases by default. So that is the problem. So basically we can have problem of deadlock in this case. And again, like XA another thing is XA does not work with serializable snapshot isolation, because in serializable snapshot isolation, we have to detect a conflict, right? It is a way of optimistic concurrency control. So you have to detect a conflict. And again, now in this case, you have to detect conflict among multiple nodes, right? So which is again a problem. Like it could be implemented, but basically again, like they need to send messages across, which is again not uh, like implemented by most databases. So yeah, so like it's yeah, so that's why mostly XA is implemented by taking locks, like these pessimistic locks instead of this optimistic locking.
Um, uh, One more thing that I've found in my experience is so there were two scenarios. I mean, there were two instances when I had to do an exactly once processing.
Mm-hmm.
So one of them was simple, like get the message from the queue and persist in a database. So
Mm-hmm.
in that case, instead of, because when you are a developer and then you know, okay, we need to do this processing exactly, you think through it, and if you know this little bit of theory, then you might think like, okay, now I need to do distributed transactions and all. But most of the times, you will be able to find an easier alternative. So in my case, I wanted to get the message from the queue and write it to the database. So what we did is, instead of doing a distributed transaction, just let make the writes idempotent. So if even if you process a message multiple times, database is gonna decline the message
Yeah.
because there are keys on that. So it was a very simple solution. And the second time was actually related with the money. So it was for an airline project. Whenever customer swipes their credit card or whenever he takes a flight, the points gonna come into his account. So in that case, we don't maintain a, so general idea is what you will do is you will create a user row and it will have a points value in it. And then multiple transactions will come and increase that points value. So then if you do that, then you need to have a distributed transaction. But there is a very simple alternative is, instead of keeping the points in a single field, just keep on adding rows in an another table. So other table will have, okay, this person has taken a flight on this date and he has accumulated 100 points. He has swiped the credit card, he accumulated 50 points. So you just keep on adding the rows there. So even if you process a message multiple times, the database has its own keys, right? So database is gonna reject if we process a particular point again.
Mm-hmm.
And what we do is, we, as and when we update that, we just update a final counter value which is on the user value. So in both the cases, because distributed transactions to go through this takes a time, right? I
Yeah.
mean, to code this, I never did that and I don't have an experience of it.
Mm-hmm.
So there are simpler alternatives available. Just you have to think a little bit, like database helps most of the times out of such scenarios.
Yeah. 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 These are very good points. Yeah. Mm-hmm. And uh, like like as you said, because these distributed transactions, they are expensive and they're not easy. Yeah, that's why generally you will find some alternating solutions, and or either you can do some compensating transaction if something fails. Like a very famous scenario which we have seen is, right, that if we are booking anything, if we are buying anything, then basically we want both of the things should happen at the same time, right? That my I should be able to successfully pay, so you should be able to successfully pay, and then the order should be placed like in a distributed transaction fashion. But because these two are completely different systems, one is the payment system, another is like booking system, and they generally belong to different companies. So if you implement a distributed transaction, it will be very expensive, right? So basically, that's why what we do is that we like, if our customer wants to buy something, we will reserve that thing for him until his payment is completed. and if his payment is rejected, then we will like then we will revert that and we will free up that thing again, right? But basically, like in ideal scenario, if we wanted to have things ideally, then our resource should not have been booked for the customer until he has completed the payment, right? Basically we have reserved that thing for him, and it might happen that he is not able to complete the payment. But how we go with the scenario is we do a compensating transaction, and in compensating transaction we like roll back whatever we have reserved for him, and like that's how we can make sure that both of the things happen. So yeah, like as you mentioned, like in most of the scenarios we generally tend to use some alternatives because of all the disadvantages and expensiveness of distributed transactions. Okay, uh, we are done from with distributed transactions. Now the next topic is consensus. Uh, Before we jump on to consensus, anyone want to mention anything else? Or
I don't get. Could you explain again? I don't get. I understand what you're saying, but the previous speaker, when he mentioned, I could you explain what he's saying?
Yeah. So what I was trying to say is mm, uh, basically if you have a project, or if you want to do something like, okay, I want to do an exactly once processing. So the messages are coming inside through a queue, and now I need to process those messages. So let's take an example of the points. So the domain is when airline wants to implement their point system. Whenever person takes a flight, you need to give points to a customer, or whenever a person uses his airline credit card, you need to give the points to a customer, right?
yeah,
So in this thing, you maintain all these points inside the database. So what happens is you have a control of your own system. So whenever a person takes a flight, you're gonna put a message in the queue and you're gonna get it. But at the same time, if there are different merchants, like airlines have a tie-up with of when I was working, there were that airline was working with near about 150 around 150 merchants. So all those merchants send their points too. And these points generally they all come into our system architecture was they all come into a queue, and from that queue we take those messages and then awards the points to the customer as and when it happens. Like we wanted to have it in a real time. So as soon as the person checks in at the gate, uh, we award him a point. Okay, he has entered the flight now, that's fine, we can give him the points. So these points were coming into a queue. And now when we say like exactly once processing, the problem is uh, so you check out a message from a queue and you write to a database. Now the failure can happen anywhere. Like you check out a message, you write to a database, and uh, before database returns you, okay, that's I have committed the message, you fail. Since the application has failed, the queue has not received an acknowledgement. So when the application comes back up, it's gonna again pull the queue and get the same message. But we have already in the first attempt we have already persisted the message. So if we process that message again, what is going to happen is we're gonna again increase the points value in the database, right?
Mm.
So this is
Yeah.
a critical problem. So to avoid that, one option is a distributed transactions, and it is like from a normal developers. I didn't know or anything about like that, or our architects even didn't know that what is the distributed transaction or how to. I mean, people heard that, but nobody knows like how to code it, and nobody has a quite confidence in it. And you are basically playing with the money, right? So in that case, what they did is instead of every transaction coming in and updating a row, so basically go to the row and increase the points by, okay, plus 20, plus 50. Instead of doing that, maintain a separate table where we used to call it as a points table. So in that points table, as and when these point messages come into a queue, we will take that message and insert it into that table. So that table basically will have, it will also give all the details. Okay, this person has taken a flight on this day and he accrued these points. He has swiped the credit card on this day and accrued these many points. So you will have all the log there, for so that you can anytime know what's happening. And when you have the log, so when the application writes a message to this log kind of a table, log in the sense is like a general logging. But basically it's just a table having all the rows. So when application writes a new row in there, it at the same time, after the row is updated there, it also goes and updates the main points. And what I was saying is, by doing this, what happens is, if the same problem, like we have checked out a message from the queue and we have written to the database persisted that, and if the application fails, it's gonna wake up again and is gonna get the same message because it has not acknowledged that. At that time, when the application tries to write that message to that points table, which is a log kind of a table, is gonna fail because it's gonna say, oh, some key constraint has followed because this message with such ID is already in there, so it's gonna fail. So nothing is going to happen. So your writes have become idempotent. So even if you process that message 10 times or more than one times, it's not going to matter. The even if with this architecture, there used to be very rare scenarios when sometimes customer would have less points or extra points than his points table. But the solution was very simple. We used to run a bad job at the end of the day, which will tally that, okay, this person has these many people have received the transaction. Let's tally. So let's do a sum of their all accrual points and check if they have correct point balances or not. So it was a very easy alternative.
Yeah, and I think it is a much better approach than doing distributed transaction. So basically, just to summarize, in the message queue, you have a message ID, a unique ID for each message, right? And on the database side, which is receiving that message, you are saying that if a message with this ID has been already processed, then you don't process it again. So it's just this simple logic, and now it's idempotent because let's say if message ID 123, it has some message, and if your application has processed that message and it fails to acknowledge, then if the queue will send that message again 123, then in the application logic you will see that this message ID 123, it has been already processed by me before, so I don't need to process it again. I can just send the acknowledge to the queue. So so that's very simple way to do it than the distributed transaction.
And the same thing we did it for the when people use their points, right? When people use their points to buy flights, the same thing. We also maintained a separate table. So this one was a accrual table. The another was a redemption table, where we used to take out their points. So accruals were in a separate table, redemptions were in a separate table, and your total will be in a separate table, which all applications query. So whenever the app query, when you log into a website, is going to show you how many points are there. So that is stored in a separate table in one line. So one user will have, okay, these many points you have at the moment.
Yeah.
Got it. Thank you.
Yeah, thank you so much for this information. Okay, uh, so I think let's move on to consensus. What is fault tolerant consensus? So basically, what is first? What is the meaning of consensus? Consensus means that one or more nodes will propose a value, and overall, a distributed system which has multiple nodes it should agree on one of those values, right? And the meaning of fault tolerant consensus is that now we have to implement this system in such a way that any of these nodes can die, and still, like, we should overall be able to, our system should work, and it should be able to propose values. Like, it should not stop working if less than majority of the nodes have died. Like, if more than majority of the nodes are working, then our system should be able to reach consensus. So this is the intention behind fault tolerant consensus, right? And so a consensus algorithm, it must satisfy these four properties, right? That, so these four properties are uniform agreement, integrity, validity, and termination. So what these properties says one by one, uniform agreement means that no two nodes decide differently. Everyone decides the same outcome, right? This is basically the meaning of consensus, that overall the system should decide one outcome, right? It should not have multiple outcomes, right? Uh, then the integrity property says that no node decide twice. What it means is that if a node has said that I am agreeing on this value, then later it cannot change its mind. Whatever it has agreed on once, it has to stick to that, right? So this is the integrity property. Validity is that if a node decides value v was proposed by some node. So basically, a node cannot, like, cannot propose, a node cannot agree on some value which was never proposed by someone. Like if I have been asked that, hey, if do you agree on A, I cannot reply back with B or C, right? Like, it should be at least proposed by someone, or it should be proposed by me, right? So this is the validity property. The termination property says that, uh, even if, so basically this termination property is related to fault tolerant, that even if the node may crash, eventually the system decides some value. And this is what makes it different from two-phase commit. In two-phase commit, we remember that uh, your transaction gets completed, so you are able to make a final decision only when every one of them agrees, right? If everyone says yes, yes in the prepare stage, then only you are able to make the decision. But in fault tolerant consensus, you need only majority of nodes, right? So uh, so this is like, these are the four properties of consensus. And now I was thinking that before we actually jump into this this theory of what the consensus algorithms are, like, I would I was thinking that we just go over this Raft's diagram of how it works in consensus, because once we go over this animation, then many of the things will get very clear, whatever has been written in the book. So have you guys seen this Secret Lives of Data Raft animation? Like, this is really good. I think it was shown in one of the presentations before, but like, just to revise ourselves, let's go over this, and then we can discuss what has been discussed in the book. Okay. So yeah, so let's go over. So basically, let's see what is the meaning of distributed consensus. So basically, first, let's forget about distributed. Let's say if we have a single node, right? In single node, if we want to agree on a value, it is very simple. Like, it is just one node. So whatever one node says, that is the value, right? So let's say this is the server, this is the client, and now the client sends 8, and now here it is, for this server to reach consensus, it is very easy because it has only one node. So it can either accept whatever client has sent, or it can reject, right? It can make a decision easily because it is the only sole owner of decision making. So Okay, now see, like now if we have multiple nodes, now the meaning of consensus here could be that if the client has sent a value 8, I will only reply the value when it has been accepted by majority of the nodes, right? So how do we come to consensus that should we accept this value of 8 or should we reject it, right? So this is the problem behind distributed consensus, that everyone should agree on one decision, whether to accept, whether to take this value or whether to not take this value, right? Uh, and Raft is one of the protocol for implementing distributed consensus. So now let's see how Raft works, and then we like most of these then shared concept we can discuss that have been discussed in the book, and that will now help us understand how other distributed consensus protocols are implemented. So in Raft, a node could be in one of the three states. Either it could be a follower. So you will see that follower is just a blue without any solids around it. A candidate has a dotted solids around it, and a leader has a solid circular circular boundary around it, right? So these are the three states. Okay, now let's look what happened. So basically, if we have these three nodes in our system, so initially all nodes are follower, and that's why you see they don't have any boundaries, right? Uh, and if these followers node, they don't hear back anything from a leader. Like if, so basically a leader has to keep sending a message to all of the followers that there is a leader in the system, right? And if they don't hear back from a leader after a timeout, then they realize that there is no leader in the system, right? So then one of the followers will try to become a candidate. So it has a dotted lines around it, right? So now by candidate, it means that I want to be a candidate for election and I want to be a leader, right? So this wants to be a leader. So it will ask the votes from the remaining of the nodes. So it will give one vote to itself, and it will ask other these two nodes whether you agree to vote on me, whether you agree to elect me. And and then the nodes will reply with their vote. If they say yes, then this will become a leader. And so now you can see a solid line around it, right? So this is the representation in this diagram. So now one of the node has become a leader, right? Yeah. Hello, I'm sorry again. My microphone got turned off, and basically, yeah. Okay. So, am I audible, right? Just to confirm.
Yes, yes.
Yes, it's audible.
Okay. So now, yeah. So now this candidate has become a leader now, right? Okay. Now, let's see. So this was the overall leader election process, right? Now let's see uh, what is the role of leader. So the role of leader is all of the changes in the system will go through the leader, right? So if a client wants to propose a value 5, then first it will go to leader. So leader will keep this value set 5, and the red means that this value is still uncommitted. This value has not been committed. So first this set 5 will be in uncommitted state, and then so this set 5 is added to a log. It is added to a append only log of this node, right? And the log entry is uncommitted, so it won't still update the node's value, right? To commit the entry, the node first replicate it to the follower node. So basically, we want to replicate it to the followers node, and once I have replicated to majority of the nodes, then only I will reply yes, right? So I will send this append only log set 5 to these other nodes in my system, right? And again, you can see here also these are in uncommitted state right now. This is red, right? So they will reply back whether they can commit or not. Uh, and then once the leader gets back this response 5, right, that they can, both of them can commit, then now it will actually commit the entry. So the leader waits from majority of nodes until it has committed the entry, right? And then it will reply, the entry is now committed on the leader and it has state 5, and now it will reply. So did you see this process was very similar to two-phase commit? Like it is not exactly, so there are some differences and there are some similarities between two-phase commit. So does anyone want to tell what are the similarities and what are the differences here?
Yeah, we have one node which is responsible for coordination.
Yeah,
Yeah.
exactly. So this is acting like coordinator. Yeah, and so and like it is, so basically you saw, right, that this happened in two phases. I don't know if I can, yeah. So basically it happened in two phases, that first it sent the messages to these two nodes, and these two nodes have still not committed the value, like it was in the red state, and they will reply back, and their reply means that they can definitely commit the value. Like if now the node says that I want to commit the value this node A, then they have to commit the value. So once this node gets reply from majority of the nodes, then it will make a decision to commit, and then it will send another message to commit. And once they receive the commit message, then only they will commit the values, right? So all of these things are very similar to two-phase commit. The difference only here is that in two-phase commit, all of the nodes in the system have to reply with yes, right? But here, this is waiting only from the majority of the nodes. So only the majority of them should reply yes, and then it can make a decision, right?
What happened that commit that the leader sends now that it got replies from all the other nodes? What if the commit never reaches the followers? The commit message from the leader.
The commit message does not reaches. Okay, so then it will have this entry in like in a state which is this node is unsure of, right? And basically what we're saying is that this node is currently disconnected from the system because all the decisions will be done through leader, right? So this node is not participating in any decision making. But once this node comes back again alive, right, when it can hear back from leader, then it can get a response from the leader, and leader can tell whether it has to commit a value or not,
I
right?
see. Okay, yeah, makes sense.
Okay, let's say make it similar to the situation that we have the coordinator, right? Let's say that uh, the main node, like the coordinator node, it received it received the acknowledge from the other node already. So it about to send the response back to the client, but it not yet, right? And the leader node crash, right? That would be the same scenario as, you know, it crashed the coordinator, right? And then what would happen?
Okay, so it has made a decision to set the value to 5,
Right.
and now it was going to reply back to the client, and and now it failed. Okay, so the client will think that the decision was not taken.
Yeah. Yeah, the client would think that the decision was not there, but the other two node was already agree with it, right?
Yeah, the thing is, in these two nodes, the value was not yet committed, uh, but in the leader it would have been committed, and now the leader has committed the value, but it has still not acknowledged it. Hmm. So yeah, so either hmm,
So let's say the client in this case, couldn't get a response from the leader, so it sent the request to node B, for example, right, and set it to 5,
mhm.
and then node B see it already 5.
No, like client. So basically, it cannot like rent. So the system will talk to a leader, right? So whatever. So if you're saying that this node is down, right? Okay. So if this node is down, then basically what will happen is the system will elect a new leader, and meanwhile there is no leader in the system yet. Client cannot directly talk to any of the nodes randomly. So there will be a small delay when the system will not be responsive when it is deciding a new leader. And once the new leader is decided, then the client can talk to that leader and uh, and basically continue. But still, I don't have answer to your this question that basically this set 5, right? So now let's say this dies, and uh, now we have these two nodes, and basically one of them become leader, right? So this node becomes a leader. So now what happens to this set 5? Whether what exactly happens here, I don't know that. If anyone else, does anyone else knows that what will happen?
As I understand, the question is if our cluster has committed changes, yeah, but response was not sent to client because of leader failure, yeah?
Mm-hmm.
Yeah, but it will similar to our classical SQL databases. I mean, like MySQL, my Oracle, if rows is committed, yeah, a
Mm-hmm.
server, it's committed in a server, but response to row to client could be lost. I
Yeah,
mean, it's similar to RDBMS, yeah.
yeah, right. Okay, yeah. So yeah, okay. The question to that answer where uh, if this value was committed here and the response was not acknowledged, then it is this same problem, right? Yeah, that in a database, that if a database has committed a value and it was acknowledging, then at that time the acknowledgement got failed, right? So client has to handle it on its end, that it has to make these operations idempotent and all such, because like these operations could fail, right? That's your point, right?
Yeah, it's yeah. I agree with you.
Yeah, so in those scenarios, yeah, the client has to make sure that these are idempotent, because if his operation was +2, then that +2 can happen multiple times if it is not acknowledged, like it's not acknowledgement. And I think that's why they have given at least the example of set. So basically, in the set value, it is okay, right? If the client is again sending set 5, then even if it is done again, it is okay. But if your operation is something like update and all, like update is also fine. You're updating to that value, but if you're like adding something, then you have to be careful that it should be idempotent.
What happens to uncommitted values if a leader fails and the uncommitted values are present in the followers? Those uncommitted values are just like purged, and like for example, node A falls and node B and node C has uncommitted values. Like set 5 is not yet committed, and say node B elects itself as one of the leader.
No, so basically, like once, I think if I will rewind it. So basically when it sets 5, first I think first it says yes to both of them, and it says the value should be committed, and then only it replies back to the client. So
No.
let's say if uh, if at this point when the value was committed on the leader, right, and
Can I
now the leader has died, right,
can I
and
interrupt?
these values were left in uncommitted state. So because these values were left in uncommitted state, so the leader has still not replied back to the client saying yes, your value was committed. So in that case it is okay, right, because I still have not heard yes from. So then I will retry, and this values, as you said, then these values can be purged or removed because these were uncommitted values.
My question was like, say two steps before this, like node A sends a node A is still the leader, and
Mhm,
it sends a message to the remaining followers,
mhm,
and the followers gets the message as set 5, but it is not committed.
mhm,
And then the follower sends back acknowledgement that, hey, we have got these values.
mhm.
Now node A, which is the current leader, falls down, like it
Yeah.
fails, right?
Mhm,
So node A has not committed anything. It's just received the acknowledgement and then it failed.
mhm,
Now node B and node C has uncommitted set 5 values in each of them.
mhm,
And node B elects itself as the leader.
mhm.
What happens to those uncommitted values? Does
Yeah,
it
yeah.
that
These uncommitted values will be removed.
be purged, right? Okay.
Will be put, yeah. So see, just your just to like again go over your point. So this set 5, and it has sent these messages to these two nodes, and it has got yes from them, right? And now so it has set its value 5, right? So now before actually sending the entry is now committed to the leader, and before actually sending success to the this client, right, it has actually first sent this commit message to both of these nodes, and then only it will send success. So after this only it will send success. So if these were in uncommitted state, then these values will be purged because still we have not replied yes to the client. So this overall process is called log replication. Uh, Now let's go to leader election.
So
So
Abhishek, I do have a question. So let's say, I mean, before leader actually reply back to the client, it send a message to these two node,
mhm,
and now it send a message to these node and send reply back to the client. But the message delivered to these node were lost. So now they don't know whether they have to commit or not.
wait, let's quickly go over here. Okay, so now so this step happened. Then uh, each log entry is currently uncommitted. Okay, now they were asked to set the value 5, but it's in uncommitted state.
Yeah.
Okay, and now, and when does it fail?
So now that leader send a message to commit the value to these two node,
These two nodes,
and
yeah.
yeah, and reply back to the client that commit
Right,
your
right.
information committed. So the information sent back to these two node to commit the value that has been lost. The leader sent that message, but somehow on those packets were lost on the network and not reached the these nodes.
Mhm. Okay, yeah. So basically, this is the same problem, right? So you are saying now it has made that decision set 5, and it will send the message to commit to these two nodes, and it will reply back to the client saying the value is committed. But you are saying, let's say this node got disconnected and it never received the message, right?
Right.
So this message was in uncommitted state on this node, right? In
Mm-hmm.
this scenario, so now this node is disconnected from the network, right? But whenever this node will come back alive again, right? It will first, like, it will see whether there is a leader in this system or not. And then it will hear a heartbeat from the leader. So when it will hear a heartbeat from the leader, then the leader will make sure that all the logs which it has are up to the latest entry when this node backs can come alive again. So basically, in heartbeat, it will send that at what level of logs currently the system is. If this is behind, then it will keep on asking the message until it can catch up and it is at the same stage as the leader. So basically, even if this message was uncommitted and even if it was lost, whenever this node comes back again, the leader will help correct it whenever it comes back alive again.
Okay, now another scenario is that when leader sent a message to this node and after send message back to the client for commit message, leader die now.
So, okay, now it has sent the commit message to these and now the leader has died, right?
Yes.
So now, then what will happen is, so this is
And this node which has the uncommitted value broadcast message for the candidate.
and now this node becomes the leader, right?
Yeah.
So this node becomes the leader now. And this message was in uncommitted state. Yeah, I don't know the answer to this.
So I can take a shot, but I'm not sure. So in Zookeeper, what happens? I know it's different, but what happens is whenever this client green one is right, so green one knows about all the three servers. That's what the quorum is. So in the client configuration, we will give the IP addresses or the host names of all these three servers. So now for the question that is being asked, the leader has not yet responded to the client and leader has died. So in that case, what client does is, so one thing is clear, right? As soon as the leader dies, someone else will be the leader, like either the node that is, I don't know their names, but the top one or the side one is going to be the leader. So what client does is since he cannot talk to the leader, he goes to the next node in his list. So client also has a list of all the Zookeeper servers. So he just tries randomly any one of them. So let's assume he luckily tries the one that is going to be a leader next time, right? So he was elected a leader and client talks to that and the connection is maintained there, right? It asks for the, I don't know the extra internals, but as we know that leader has sent the value to both the followers. At the same time, leader has also sent them a commit message, right? And then leader died before responding to the client. So these both of the followers have received a commit and they now have a final value, but leader has died. So when the next time client going to connect to a new leader, leader is going to respond to it, think that, yeah, we have committed the value. Does it sound convincing?
Not sure I followed you fully.
Yeah. So what I mean by that is, if so, one thing to keep in mind is the client, the green one, right? The
Mm-hmm.
client not so client talks to the leader. That is one thing, and at the same time, client also knows about the other members of the quorums. So when the leader dies, client will talk to any other member of a quorum. If
Okay.
that is not a leader, it will go to the next entry. and when it stumbles upon a leader, it will talk to that node or that member of a quorum. And now, since
But that is not how actually raft work, is that?
yeah, I am talking from a perspective of a zookeeper, which is
Okay.
using different. But in the client, when we configure a client, right?
Mm-hmm.
So you want to talk to a zookeeper quorum. When you configure a client, the client we give the addresses of all the members of a quorum,
Okay.
and the client only talks with the leader. So if anytime the leader fails, it tries the next entry in the list.
So what will happen in that scenario, what we were discussing? So client received the message from the leader that value has been committed, but these node did not receive the commit message, and before that leader died. And now client know that my value has been committed because it received the response from the leader before he actually leader died.
What I wanted to say is client, the leader will not respond unless these majority in the quorum has committed, the majority people in the quorum has committed. So if leader,
So you are saying that there are two message will float. First, first leader will send the uncommitted value so that client can put the value in the log, and then leader will send the another message to commit the value.
yeah.
Okay.
Okay, yeah, I'm okay. Yeah, I'm not sure about this point. Okay, but yeah,
Yeah.
good point. So what you are saying is that now before responding yes, it will send the commit message to all of these nodes, and it will wait for the acknowledgement of this message from the quorum of these nodes. When it receives the acknowledgement, then only it will reply yes to the customer.
Though I'm not sure, but I'm thinking the scenario. Let's say leader send the message to these node for the log, and the only one node receive that message and put that in the log, and another does not receive the message, or somehow response get lost. And now leader send the message. Leader send the message for the commit, and now this time it actually reach the another node, but not the first one which received the value. Now what will happen?
So what happens is like in these protocols, they do a guarantee like the messages will come in order. That's the whole system is relying on this assumption, like the messages will be always in order. You cannot say like I missed a message number 10 and I got a message number 11, because what
Yeah,
these
that is fine. That these follow the total order. But my point is that let's say this guy actually broadcast the message to these two for committed, and somehow this message does not reach here, but reach here. And now this guy actually send the message to commit the value, and now this time it actually does not reach here, but reach here. And now this guy does not know about that. What is that message for?
So every message is accompanied by ever increasing number, which is sequentially increasing, like number 1, 2, 3, 4, like that. So
Mm-hmm.
there is a gap in between. The follower knows that, okay, I missed a message.
Yeah,
Okay.
yeah, that's a very good point. Yeah,
Yeah.
actually, yeah. Mhm.
So yeah, that's fine. So in that case, it will not actually. So you are saying that in that case, it will ignore that message, or maybe request for the missing message.
Yeah, yeah. And so then the leader has that missing message, right? So it will first send the missing message first, which this one, which was incomplete, and
Mm-hmm.
then it will actually send the new message.
Okay. Yeah. Thank you.
Okay. Yeah, I think it's 9, so let's discuss this in again in more details. Yeah, and if anyone has any questions, then let's post it on Discord so that we can take up those scenarios next time. Okay. Thank you, everyone.
Yeah, thank you, Abhishek. Yeah.
Thank you.
Thank you. Abhishek.
Thank you.
Can somebody make me a host?
Yes, I'm gonna make you host.
Thank you. And